Imagine holding your laptop for just a second. It weighs barely more than a book. Yet inside that slim metal shell lives billions of microscopic transistors working together billions of times every second. Every email you send, every movie you stream, and every game you play depends on a manufacturing journey that begins thousands of kilometers away from the nearest electronics factory. But here's what nobody tells you. Your laptop was born long before engineers ever assembled it. It began deep beneath mountains, inside blazing furnaces, and some of the world's most advanced cleanrooms. Today, we're following that incredible journey from the Earth itself to one of the most sophisticated machines humans have ever built. Think about this. More than 225 million laptops leave factories every year. Yet very few people ever see where they truly come from. A single laptop contains aluminum, copper, gold, silver, silicon, lithium, cobalt, nickel, rare earth elements, glass, plastics, and dozens of highly engineered materials. Each one travels through a global supply chain stretching across continents before meeting on a production line that runs with almost unbelievable precision. And this is where our journey begins, in places most people will never visit. Most people never think about this, but the heart of every laptop begins as ordinary sand. High-purity quartz mined in countries like the United States, China, Norway, and Brazil contains silicon dioxide. After refining, manufacturers produce electronic-grade silicon with a purity reaching 99.9999999%, often called 9 nines. That astonishing level of purity means even a few unwanted atoms can ruin an entire semiconductor wafer. Most people never think about this, but the heart of every laptop begins as ordinary sand. High-purity quartz mined in countries like the United States, China, Norway, and Brazil contains silicon dioxide. After refining, manufacturers produce electronic-grade silicon with a purity reaching 99.9999999%, often called 9 nines. That astonishing level of purity means even a few unwanted atoms can ruin an entire semiconductor wafer. Now imagine another journey happening at the same time. Huge bauxite mines in Australia, Guinea, and Brazil produce the ore that eventually becomes a lightweight aluminum body of many premium laptops. The ore travels thousands of kilometers to giant smelters where electricity separates pure aluminum from oxygen. Producing just 1 kilogram of aluminum can require around 14 kilowatt-hours of electricity, making it one of the most energy-intensive materials inside your computer. The battery tells an even more remarkable story. Lithium often begins its life beneath the salt flats of Chile and Argentina, or inside hard rock mines in Australia. Cobalt, another essential battery ingredient, is largely mined in the Democratic Republic of the Congo before traveling to sophisticated refineries in Asia. Nickel from Indonesia and Canada joins the mix, creating a carefully balanced chemistry capable of powering your laptop for hours. Copper forms the invisible highways carrying electricity through every circuit. Some of the world's richest copper deposits lie beneath Chile, Peru, and the United States. After crushing, flotation, smelting, and electro-refining, manufacturers create copper with a purity above 99.99%. Imagine thousands of microscopic electrical pathways spreading across a motherboard, each one thinner than a human hair, but carrying signals at astonishing speeds. Then come the precious metals. Gold from Australia, China, Russia, Canada, and South Africa protects electrical contacts from corrosion. Silver improves conductivity, while tiny amounts of palladium and rare earth elements enhance specialized electronic components. The shocking part? All the gold inside one laptop weighs less than a fraction of a gram, yet its reliability makes it worth every microscopic particle. Glass begins as carefully selected silica sand mixed with soda ash and limestone before melting inside furnaces hotter than 1,600 degrees Celsius, or about 2,912 degrees Fahrenheit. Engineers cool the molten glass with extraordinary precision to eliminate internal stress before cutting sheets thin enough for brilliant laptop displays. Every surface must remain almost perfectly flat because even tiny imperfections become visible once millions of pixels light up. Even the plastics hide incredible engineering. Manufacturers combine petroleum-based polymers with fiberglass, flame retardants, and precision additives to create components that stay strong, lightweight, and heat-resistant for years. Every material must survive thousands of opening and closing cycles, sudden temperature changes, and accidental drops without cracking. What happens next surprised even experienced engineers, because these raw materials are about to enter one of the cleanest manufacturing environments on Earth. Now the real magic begins. Imagine walking into a semiconductor fabrication plant, where the air is cleaner than a hospital operating room. Engineers wear full-body cleanroom suits because a single speck of dust can destroy a microchip containing billions of transistors. Most people never think about this, but the tiniest particle floating in the air can cost thousands of dollars in lost production. The journey starts with flawless silicon crystal called an ingot inside crystal growing furnaces operating at nearly 1,420 degrees Celsius, 2,588 degrees Fahrenheit. Molten silicon slowly forms into a single crystal that can weigh more than 100 kilograms. Diamond wire saws slice the ingot into wafers only about 0.7 millimeters thick. Every cut must stay incredibly precise because even microscopic vibrations can ruin the surface. Next comes photolithography, the process that gives every processor its incredible intelligence. A light-sensitive chemical called photoresist coats each wafer before extreme ultraviolet lasers project circuit patterns far smaller than anything your eyes could ever see. Some features measure less than 3 nanometers, thousands of times thinner than human hair. What happens next feels more like science fiction than manufacturing. Layer after layer, engineers build billions of transistors using plasma etching, ion implantation, chemical vapor deposition, and atomic-level polishing. Powerful vacuum chambers operate at pressures thousands of times lower than Earth's atmosphere, while plasma reaches temperatures hotter than the surface of the sun. Yet every process lasts only seconds or minutes before robotic systems move the wafer to the next machine. The entire sequence may repeat more than 1,000 times before a chip is complete. Meanwhile, another factory produces the motherboard that will connect every component together. Giant rolls of copper-clad fiberglass laminate enter automated production lines, where CNC drilling machines create thousands of microscopic holes at incredible speed. Chemical baths remove unwanted copper, while precision plating forms electrical pathways capable of carrying signals at billions of operations every second. The smell of chemicals, the hum of motors, and the flashing inspection lights fill the factory floor. Now imagine watching high-speed pick-and-place robots moving faster than your eyes can follow. Using vacuum nozzles, they position tiny resistors, capacitors, memory chips, and processors with an accuracy measured in microns. Some advanced machines place more than 100,000 electronic components every hour, never slowing down, never losing concentration. The clicking sound of robotic arms create a rhythm unlike any other factory on Earth. After placement, the boards enter a reflow oven where temperatures climb to approximately 245 degrees Celsius, 473 degrees Fahrenheit. Tiny solder paste particles melt into shining liquid metal before cooling into permanent electrical connections within minutes. Think about this. The processor inside your laptop now becomes physically connected through thousands of microscopic solder joints, each one essential for perfect performance. If even one connection fails, the entire motherboard could stop working. While electronics come together, another production line machines the aluminum chassis. High-speed CNC machining centers spin cutting tools at up to 30,000 revolutions per minute, carving solid aluminum blocks into incredibly thin yet rigid laptop frames. Coolant sprays continuously to control heat, while robotic arms transfer each part from one station to the next. Bright aluminum chips scatter like silver confetti beneath the machines. The display assembly demands extraordinary precision. Layers of ultra-thin glass, liquid crystal or OLED panels, polarizing films, and protective coatings come together inside dust control rooms. Automated bonding machines apply perfectly measured adhesive, while laser alignment systems ensure every layer sits within fractions of a millimeter. You never see this hidden engineering once the screen lights up, but every pixel depends on it. Finally, everything meets at the main assembly line. Skilled technicians and collaborative robots install the motherboard, cooling system, battery, speakers, keyboard, touchpad, wireless antennas, display, and precision screws in a carefully choreographed sequence. Every movement follows digital instructions displayed in real time, reducing assembly errors to almost zero. And just when you think the laptop is finished, the toughest challenge is still waiting. You might think the laptop is finally finished, but this is where the real test begins. Every completed unit enters a world where even the smallest flaw can mean instant rejection. Imagine a production line where artificial intelligence, laser scanners, and human experts work together, searching for defects so tiny they measure just a few microns. What happens next surprised even experienced engineers. The first inspection happens before anyone even touches a laptop. High-speed AI vision systems capture hundreds of images from every angle in just a few seconds. Advanced algorithms compare each image against a perfect digital model, detecting scratches, dents, missing screws, connector damage, or color variations that the human eye could easily miss. Some systems inspect more than 1,500 laptops every hour, never blinking and never getting tired. Next comes electrical testing. Robotic probes instantly connect to dozens of test points across the motherboard, checking voltage, resistance, signal timing, USB ports, memory, Wi-Fi, Bluetooth, speakers, microphones, and charging circuits. Thousands of measurements happen in less than 2 minutes. Imagine hearing hundreds of tiny electronic clicks, while every circuit proves it can perform flawlessly. Now the processor faces intense stress. Automated systems push the CPU and graphics processor to 100% low for hours, while powerful software monitors every sensor. Temperatures often climb above 90 degrees Celsius, 194 degrees Fahrenheit, as cooling fans accelerate to more than 5,000 revolutions per minute, creating a steady rush of air throughout the testing chamber. Engineers watch carefully because one unexpected temperature spike can reveal a hidden manufacturing defect. Then comes one of the toughest challenges of all, the environmental chamber. Laptops experience freezing temperatures near minus 20 degrees Celsius, minus 4 degrees Fahrenheit, before moving into scorching conditions above 60 degrees Celsius, 140 degrees Fahrenheit. Engineers repeat these cycles again and again to simulate years of real-world use in deserts, mountains, offices, and freezing winters. Most people never think about this, but your laptop has already survived whether you may never experience. The keyboard enters its own endurance marathon. Robotic fingers press individual keys hundreds of thousands, sometimes millions, of times while precision sensors measure every movement. Hinges repeatedly open and close until they complete tens of thousands of cycles without developing excessive play. The constant tapping echoes to the laboratory like dozens of invisible typists working day and night. And this is where human skill still beats machines. Experienced inspectors gently run their fingertips across the aluminum body, checking for imperfections too subtle for automated sensors. They listen to the sound of the hinge opening, feel the smoothness of the trackpad, and verify the alignment of every panel. Years of experience allow them to notice tiny differences that even advanced algorithms sometimes overlook. Every factory also measures quality with astonishing precision. Laser measuring systems verify dimensional tolerances, often within plus or minus 0.05 millimeters, while rejected units move automatically to engineering teams for investigation. Depending on the product and production stage, final defect rates can fall well below 1%, thanks to continuous monitoring and internationally recognized quality systems, such as ISO 9001. Every rejected laptop teaches engineers how to build the next one even better. Only after passing every inspection does a laptop receive its software, final calibration, protective packaging, and shipping label. It looks calm and ready, but behind that polished finish lies one of the most demanding manufacturing journeys on Earth. Yet one mystery remains. Just how many of these incredible machines does the world build every year, and which countries lead the race to create the future of computing? Now that you've seen how a laptop is built, imagine the scale behind this industry. Manufacturers produce well over 225 million laptops every year, and together they generate a global market worth well over $150 billion annually. If you place 1 year's production end to end, the line would stretch for thousands of kilometers. Every single day, hundreds of thousands of new laptops begin their journey toward homes, schools, laboratories, and businesses around the world. Although the raw materials come from nearly every continent, most final assembly happens in Asia. China remains the world's largest laptop manufacturing hub, followed by major production in Taiwan, Vietnam, Thailand, and India. Thousands of suppliers work together like one giant machine, delivering processors, displays, batteries, memory, and aluminum housings at exactly the right moment. Think about this. If even one supplier stops for a day, entire production lines can slow to a crawl. The industry also supports millions of people worldwide. Engineers design processors measured in nanometers. Miners extract valuable minerals from deep underground. Technicians assemble delicate electronics. Software specialists write testing programs. And logistics experts move products across oceans. Most people never think about this, but a single laptop represents a combined effort of thousands of individuals spread across dozens of countries. The story began more than 50 years ago. Early portable computers weighed several kilograms, offered only a fraction of today's performance, and cost far more than many families could afford. Now, a laptop thinner than a notebook can perform billions of calculations every second while running for hours on a single charge. What once filled an entire room now slips effortlessly into a backpack. And this is where it gets truly extraordinary. Engineers are already building the next generation with artificial intelligence accelerators, advanced 3D chip packaging, recyclable materials, and batteries that charge faster while lasting longer. Future factories will rely even more on autonomous robots, AI inspection systems, and digital twins that predict problems before they happen. The laptop of tomorrow is already taking shape inside today's research laboratories. From grains of quartz buried beneath ancient rock to billions of microscopic transistors switching faster than the eye can imagine, you follow one of the greatest manufacturing journeys ever created. Every aluminum panel, every battery cell, every precision screw, and every line of circuitry reflects decades of engineering, relentless testing, and remarkable human creativity. The next time you open your laptop, you won't just see a computer. You'll see the combined effort of miners, scientists, engineers, technicians, robots, and innovators working together across the globe. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.